Welcome to my associated panelists. We hope this is going to be a great discussion, talking about really the future of where computer science is heading. And what I'd like to begin with is a short description of my work most recently. I've become the principal investigator on a project with the Baylor College of Medicine to improve the way that we do cancer research using the types of cognitive computing technology that Watson brought to bear on the Jeopardy challenge. And working on this project has really inspired me and made me realize that there is a significant problem in science today, all sciences, not just biology, in the sense that they really don't scale anymore. If you think of the way that science has always been done, if you're a new graduate student coming into an area and your thesis advisor comes in to help you choose the topic of your research, he's going to dump on your desk thousands of papers on the particular area of specialty and say, first go read all of these and then we can figure out where you should do your research. That's not really practical anymore. It's not even going to be practical today, and it's certainly not going to be practical in the future as more and more information becomes available. Every science is going to need the assistance of a computer like Watson that can understand all the critical elements in a domain, make sense of them, and figure out where are the gaps, where are the new hypotheses that should be worked on, what are the new tests, the new experiments that should be run. And the ingredients are all there today. It's really a combination of the big data capabilities, the analytics, the visualization and modeling, combined with the capturing of the domain knowledge and expertise to create what I consider to be an accelerated discovery solution. And I believe that this combination is going to make machine analysis of scientific knowledge not just possible, but inevitable, and it's going to be essential if we are going to make the next level of defining disruptive technological and societal leaps. So that's my thesis, and I'm really interested to hear what the other panels think of that and what thesis they come together with for the future. John?
Hi, I'm John Martinez, UC Santa Barbara, and I'll be talking about quantum computing. For about 20 years now, a little bit more, physicists, mathematicians, computer scientists have been trying to figure out how we can use the laws of quantum mechanics to more powerfully manipulate data. The basic idea is normally we think of a bit as a value as 0 or 1, but in quantum physics, it can be both 0 and 1 at the same time in some kind of quantum superposition. And the reason this is interesting and important is if you put a lot of qubits together, you could then potentially make a fantastic parallel processor of processing all these possible combination of bits, so that the parallel processing power is going to go as 2 to the number of qubits. It's exponentially powerful. Just to give you an example, you have 300 qubits. You then have a parallel processing ability 2 to the 300 power. That's more than there are a number of atoms in the universe. That's clearly something you could never do classically. Now, to take advantage of this is a lot of work. Physicists have been working on it really hard for 10, almost 20 years now. The variety of systems. We're talking about here building superconductor systems that we build with integrated circuit technology, operate at low temperature. They look like normal electronic devices that we build based on superconductivity, but the difference here, because of quantum mechanics, it's not just the current. You have a classical current flowing in a wire, you can have a current in the wire that's both flowing up and down at the same time, just like you see in quantum mechanics, just like when you say that there's an electron cloud around a nucleus where the electron can be on one side or the other. And this allows this parallel processing ability. We've had a really amazing breakthroughs in our field the last few years, and then especially last year at our lab. We now can have quantum bits which have the best logic gate performance. We can build quantum logic gates out of it. We have the best performance of the world. We made huge improvements. If any of you know about the D-Wave quantum simulator or quantum annealer, we're about 1,000 times a longer memory time than their devices. Of course, what's interesting about this system is that once you understand how to make the basic elements, you can then scale up to many qubits using standard IC fabrication. And we've been working hard for the last 10, 15 years to figure it out. We think we know how to do it. So we think there's a lot of neat applications we can do in the future. Just mention three. One, quantum simulation of physics systems using the power of this. Some kind of quantum analog computation. D-Wave has kind of been looking at that, maybe touches on a lot of the ideas talked about in this section. And finally, three, quantum digital applications. We hope that by pushing forward on these ideas, we can then build a really new powerful quantum computer in the next few years, 5, 10 years.
Thanks, John. Max?
Thanks. My name is Max Schulocker. I work at Stanford University under the direction of Professor Subhashis Mitra and Philip Wong. And we work on carbon nanotube transistors. So when you look at the trend of electronics over the last couple of decades, I haven't been around for it, but if you look at the trend, then it would have predicted that today, our computers today would have tens of gigahertz processors in them. And that's clearly not the case. And why is that? Well, if you look at what's been driving the semiconductor industry, it's really been Moore's law, right? You scale devices smaller, you make smaller transistors, you can fit more in your chip. And the really cool thing about Moore's law for the last couple of decades has been as you made things smaller, they also became faster and more energy efficient. So it was a win-win solution. It was a free lunch. But now we're reaching a stage in this last 10 years or so where Moore's law is still continuing. We keep scaling devices, but silicon is reaching fundamental limitations where it is no longer becoming more energy efficient as we scale our devices. And this sets a limitation to how far you can scale silicon. And it's not a question of if Moore's law will come to an end for silicon, but when. And thus, our work focuses on carbon nanotubes as kind of the next generation of technology to further improve computational power. And not just computational power, but energy efficiency. Because I just don't want the next version 2.0 of IBM Watson. I want to have the power of IBM Watson in the palm of my hand without burning a hole through my pocket. So you need a technology which is both increased computational power and energy efficiency. And that's where carbon nanotubes come in. So carbon nanotubes, the motivation is there. We're not talking 20% increases. We're talking 10x or more benefit in performance or energy efficiency. You're talking about technology which can scale an additional 2 to 3 technology nodes beyond where silicon can scale. And additionally, new architectures are available if you go to carbon nanotube technologies. So as an example, you can build monolithically integrated 3D circuits. So why is this cool? Well, now I can build a layer of circuits on one layer, a second layer of circuits, a third layer of circuits. You have logic on logic on logic on logic. But what's really cool is you can actually integrate this with memory now. And this is stuff that we've done, where you can have logic and memory, three-dimensionally, monolithically integrated for very, very tight integration of memory and logic to really overcome this memory bandwidth obstacle, which everything's facing now, especially with big data. So, and most recently, you have to ask yourself for an emerging technology, it's promising, and is it realistic and feasible? So carbon nanotubes, we've been able to show now very recently, are also a very feasible and manufacturable technology with a demonstration of a basic computer built entirely out of carbon nanotube transistors. So I'm excited about carbon nanotubes because it's both promising and a very realistic technology. Thanks.
Thank you, Max. Umesh?
Hi, I'm Umesh Vazirani at UC Berkeley. Let me try to step back and put all this in context. In the early part of the last century, we had the start of what's being called the first quantum revolution, which allowed people to understand the world around us at a much deeper level and led to things like semiconductors and lasers, which power our world today. But over the last couple of decades, we've had the beginnings of what's being called the second quantum revolution, which is where actually, instead of just looking and understanding what nature gives us, there's an ability to pattern matter at a completely different level. But once you start doing this, you start realizing that there are completely new capabilities that you have. So, for example, it gives you completely new levels of security that are possible because of things like the uncertainty principle. It's possible to generate truly random bits, certifiably random bits. And then it, of course, leads to exponential computing power and a potential way to get past Moore's law. Now, of course, from a theoretician's point of view, this is a magnificent playground because you have these properties that you can only dream of, entanglement between quantum systems, which have a property called monogamy, where qubits that are entangled with each other cannot be entangled with anything else. And then you can start thinking about how to make use of these properties. But then you could ask, well, why should why should you worry about it in terms of, from a practical viewpoint? Well, probably the biggest, very good example of this is what happened this summer with this company D-Wave. Google purchased their machine. Now, the reason I would say this is very interesting is not because it was a great machine. In fact, I think it was a terrible machine. But the reason that it's so interesting is that there's such a pent-up demand for things quantum because they are interesting. They are that even something that experts think of as being not very good at all, not doing very much, is something that has been extremely successful. And of course, this is really the tip of the iceberg because there are many other directions that people have been exploring which are much deeper than that. Now, the other aspect of this that I should say is that one thing that may not be quite as well understood about quantum computing is that in addition to the hardware of it, the algorithms are really the key. And in fact, the shortcomings of the D-Wave machine, whatever else they were, really lie on the algorithm side. Now, where do quantum algorithms really lead us? Well, if you look at one of the biggest aspects of the use of computers, it's really one of the biggest uses of computer cycles is in physical simulation of the physical world. But as you go down to the nano level, you have to start taking quantum effects into account. And this is where the exponential power of quantum computers comes back to bite us, and in fact, it becomes an exponential overhead in simulating these systems. And so how do you do that? Well, there are two different options you can use. One is you could try to design special purpose quantum computers, and there are various efforts to do that, as John talked about. And then there's another direction you can go with this, which is with the study of quantum computing, there are being developed new classes of classical algorithms that you could run on your computers today to simulate quantum systems extremely fast.